From the early work we've done in this course, we know that we can start an angle in standard position, which means putting its initial side here on the positive x-axis, and then go around in a circular motion until we get to a second line segment, which we call its terminal side. We tend to use the Greek letter theta to represent this angle or the size of the angle, although we could also use phi or alpha, or really any sort of variable that we want. Theta tends to be the one that's used the most. One of the nice things about trigonometry is that it doesn't matter what the radius of this circle is. The sine, cosine, tangent, and so on of this angle will be the same regardless of the size of the radius. If we restrict the radius to 1, then it's our convention, as we learned in section 5.1, to track our movement along the edge or the circumference of the unit circle instead of somewhere randomly in the middle or anywhere else for that matter. Let's make an interesting observation. Remember the formula that we came up with? It's been a while now. S equals r theta. That told us that the length of the arc cut out by an angle. Let me just use a different color and I'll show you the angle here. This is the central angle theta. The arc cut out by that angle has a length of r times theta. Well, r for the unit circle is 1. So for the unit circle, S is just equal to theta. That means that the length of the arc has the same numerical measure as the size of the angle. Also in 5.1, we started calling theta t, and we referred to theta bar, which I haven't really been using, but we know that to be a reference angle. We started calling that t bar and called it the reference number. So the reference angle and the reference number have the same numerical value. They're just a different perspective on the situation. And the angle theta and the distance traveled by a point to get from 0 to the terminal point of angle theta are also equal, numerically speaking, and again, are just different perspectives on the same thing. Calling the angle t is just the use of a different variable, at least in one sense. So if we have x is equal to r cosine theta and y is equal to r sine theta, we can adjust this just a little bit to find a different way to write this. First of all, I'll write theta as t, and then while I'm at it, I'll make the observation that I'm only doing this because I'm in the unit circle. T is the name for theta when I'm in the unit circle. And because I'm in the unit circle, the radius is 1, so I can erase those. While I'm here, I'll make the observation that the tangent of t is equal to the sine of t over the cosine of t, and that's y over x. Of course, the cotangent of t is just x over y. The secant of t is just 1 over x, and the cosecant of t is 1 over y. And I got those just by flipping over. Cosine of t is 1 over secant, so 1 over x is cosecant. Sine is 1 over, cosecant is 1 over sine, so cosecant is 1 over y. As we noticed before here, we have to be careful that x is not 0 and y is not 0. When we were doing this before, we also observed that r had to be greater than or equal to 0. But again, in this particular case, we're in the unit circle, so r is going to be equal to 1. Therefore, it's guaranteed to be greater than or equal to 0. Now, the main reason for talking this through this way is so that you can see how, well, one reason anyway, is so that you can see how we might evaluate the tangent of t as opposed to the tangent of theta. Well, t is just equal to theta, right? So we're just going to say that the tangent of t, where t equals pi over 6, is the tangent of pi over 6. We can either look this up on a table, or we can say that the tangent of pi over 6 is equal to the sine of pi over 6 over the cosine of pi over 6. And the sine of pi over 6 is a half, and the cosine of pi over 6 is root 3 over 2. So either way, I get 1 over root 3. The main difference between what I've just done and what we've been doing before is that we're looking at it somewhat more numerically. Here's the angle pi over 6. It has coordinates cosine of pi over 6, sine of pi over 6. And that's equal to root 3 over 2, comma, 1/2. That's my x and my y. Now, if I know those values, I can use the x value to find the cosine of that angle, the y value, the y coordinate, to find the sine of that angle. Y over x gives me the tangent of that angle, and so on. Here's my y over x. So again, really, we're just doing the same things as we've done before, but with a slightly different perspective. The next thing in your textbook is a table, a blue box with a table containing special values of the trigonometric functions. Well, we already have this table. In the case of the textbook, they put the angles down the side, and whether it's the sine, cosine, tangent, cosecant, secant, or cotangent across the top, and then they fill in the chart from there. I tend to do it so that the angle is across the top and the relationship, the ratio, sine, cosine, or tangent, is down the side. But you get the same entries either way. You get the same entries as you did when we were doing this from the perspective of angles rather than from the perspective of numerical entries. The other thing that your textbook mentions at this point is domain. The domains of the 6 different functions are, well, sine and cosine are all real numbers. And then it tells us that tangent and secant have domains that are all real numbers except for pi over 2. You can't plug pi over 2 in for tangent or secant. Now, it doesn't really say why, and I can explain why, but I think it's much, much easier to do when we start graphing trigonometric functions. So I will hold you accountable for the domains of these functions, but not just yet. When we start graphing in section 5.3, then we'll talk about domain, and after that, you'll be responsible for understanding the domains of these functions. The good news for you is that that doesn't happen until after the first exam. So for the first exam, you don't have to worry about the domains of these functions, but for the second one, you will. All right, like I did in section 5.1, I'm just going to have one video here, I think. The second subsection, which would normally be the second topic, is called Values of the Trigonometric Functions. And for the most part, we already know how to do this. We're just taking a slightly different approach. However, there is one very big important idea in that subsection that I want to address. So I am going to make a second screen for this video called Values of the Trigonometric Functions, but really that's going to be about one particular thing. We've already learned that when you find the sine of any angle, if that angle is in quadrant 1, its sine will be positive. If it's in quadrant 2, its sine will be positive as well. If it's in quadrants 3 or 4, though, the sine will be negative. The cosine of any angle in quadrant 1 will also be positive. In quadrant 2, though, the cosine of an angle is negative. In quadrant 3, it's also negative. And in quadrant 4, the cosine of any angle in quadrant 4 will be positive. And the tangent, well, the tangent is positive in quadrant 1, negative in quadrant 2, positive in quadrant 3, and negative in quadrant 4. So we said that all trigonometric ratios are positive in quadrant 1, only sine is positive in quadrant 2, only tangent in quadrant 3, and only cosine in quadrant 4. Remember that the sine, saying that the sine, S-I-N-E, of an angle in quadrant 2 is positive also means that the cosecant of that angle would be positive. The tangent and the cotangent of an angle in quadrant 3 is positive, and the cosine and the secant of an angle in quadrant 4 will be positive. Your textbook then goes on to give a couple of examples of how to evaluate trigonometric functions. For example, it's in example 2, one of the problems is that they want you to find the tangent of negative pi over 3. We haven't actually talked much about negative angles yet, but this is a really good opportunity. So the size of the angle is pi over 3, and if it were positive, it would be up here. But it's not positive. It's negative, so I need to go in the opposite direction. So I'm going to go along, I use a pen, I'll go around in the negative direction, pi over 3, so I get to about here. This is negative pi over 3, and it has another name. We've been calling it, let's see, this would be 3 pi over 3. All the way around would be 6 pi over 3. If I subtract 1 pi over 3 from 6 pi over 3, I get 5 pi over 3. So this angle can actually be called either 5 pi over 3 or negative pi over 3. There's a reason for having two names here. We'll get to that in a little while. But what is the tangent of negative pi over 3? Well, we know how to do that. What is the tangent of pi over 3? Positive pi over 3. I'll just do that by saying it's going to be plus or minus the sine of positive pi over 3 over the cosine of positive pi over 3, because tangent is equal to sine over cosine. So it'll be either positive or negative. Now, the sine of pi over 3 is the square root of 3 over 2, and the cosine of pi over 3 is a half. If I invert this second fraction and multiply, the result is that the 2's cancel. So if you have a complex fraction and the denominators in both of the inside fractions are the same, you can cancel them. So right now I have that it's either positive or negative, the square root of 3 over 1, or I think I'll just write it as the square root of 3. Now this plus or minus business has to do with which quadrant I'm in here. We know that tangent is positive in quadrant 1 and in quadrant 3. Everything's positive in quadrant 1, but only tangent and cotangent are positive in quadrant 3. We are in quadrant 4. Only cosine and secant are positive there. Tangent must be negative. So I have negative the square root of 3 as my answer. Now that's no different from what we've already done, so I'm not going to spend much more time here. That's another example, and I'm really glad I had a chance to show you how to deal with a negative angle, but really, we haven't done anything new here. If you're dealing with nice angles, 30, 45, 60, 0 or 90, or any multiple of those, anything that has a reference angle in any of the four quadrants, then I'm going to expect you to do your work as an exact value and give me values, give me answers that look like this. But sometimes you'll be asked to do problems like find the cosecant of 2.7. And in that case, you're going to have to use your calculator. One of the very, very important questions you're going to need to ask yourself, though, is this in degrees or is it in radians? And the answer is, in the absence of a degree symbol, it's in radians. Also, to actually work this problem, you're going to need to figure out what the sine of 2.7 is, and then divide 1 by the result. Okay, again, none of this is new, although it's a really good review. The thing I do want you to take away from this subsection is something about even and odd properties. And it's important enough that I think it deserves its own screen, if not its own video. I'm not going to make a whole separate video, but I will go to a different screen so that it's easy to find later on. This is one of those concepts that is much more easily explained when you can see graphs. So I'm going to describe the process using familiar graphs, x cubed, x squared, things like that. And then we're going to come back and revisit it once we know what the graphs of sine and cosine look like, sine and cosine and all the others. But for right now, I just want you to have an idea of what an even and an odd function are. An example of an even function is y, or f of x, equals x squared. And here's why. Here's what x squared looks like. Oh, I'm having trouble drawing it. There we go. There's y equals x squared for some scale. If I take a value of x, and I take a value of x on the other side that's the same numerical value, but the opposite sign, then in both cases, I get the same positive y value out. What that means is that f of x is equal to the same function, the y value you get here, is equal regardless of whether you plug in a positive x or a negative x. So by definition, we say a function is even if this is true. Here's an odd function, y equals x cubed. This one's a bit weirder, but it helps me remember to use y equals x cubed. Because here, if I take an x and a negative x, I get out the same numerical value for y, but the opposite sign. So if I plug in a positive x and I plug in a negative x, I get the opposite sign. Another way you see this sometimes is negative f of x equals f of negative x. And I can get that by just multiplying both sides of this equation by -1. All right, I'm going to retain this version of this formula, because that's the more common way you see it written. Now there's a table near the bottom of page 414 in your textbook, and it gives you some kind of formulas. Sine of negative t is negative sine of t, cosine of negative t is cosine of t. But those are all kind of, I don't know, it looks like some stuff you have to memorize, but you don't necessarily aren't necessarily going to understand what it's telling you. Except that if you look at the sine of negative t equals negative sine of t, you get this. Sine of negative t equals negative the sine of t. And that format is the same as this one here. So what that tells me is that sine is an odd function. The cosine one is the other one you commonly see, and that is that cosine of negative t, I'm putting that on that side, is equal to the cosine of t. And that has the same format of this. The input here is positive, the input here is negative, and they're equal. So what that tells me is that cosine is an even function. Now, if you graph these, and we haven't done that yet, but if you graph these, it's so much easier to see and explain what's going on. With the even function, it's really easy to see that you plug in an x, you plug in a negative x, you get the same y value out. There's this symmetry almost around it is a symmetry around the y-axis. It's a little harder to see here. The symmetry is actually along the line y equals x. So now it's starting to get a little bit muddy, and without being able to graph these functions and show you graphically what's happening, I don't think I really want to get into the weeds with this just yet. But consider this something of a heads up. We will come back and revisit this property when we know how to graph these functions. The last topic or subsection in this section of the textbook is fundamental identities. But again, we've really done this. The only difference is that instead of calling the angle theta, I'm calling it t. Here are my reciprocal identities. Here are my Pythagorean identities. Replace t with theta and you have the same table. Okay, I've written it in a different order. I think I had them all up in the top right-hand corner the last time. But you have the same table, you have the same information as you did before. There's nothing new to memorize here. In fact, remember that I think you really only need to remember these ones and this one, and pretty much everything else falls out from that. There's another example here of writing one trigonometric function in terms of another, and they use pretty much the same technique. And there's also another example of finding one trigonometric function if you know the value of another. So if you know that the cotangent of theta or the cotangent of t is 3/5, then find the secant, or find the cotangent, or find the cosecant of the same angle. Well, we've already done that. We did that in section 6.3, right? We're doing this. We did several sections in chapter 6 before we took on chapter 5. And we're going to go back to chapter 6 and go back and forth between chapter 6 and 5 a little bit more here. But we've already done these things. We don't need to do them again. If you do want to review, you're looking for the video called Trigonometry, Trigonometric Functions of Angles, Trigonometric Identities. And I talk about the first of these approaches at about 28.5 minutes into that video. This is the one that came from section 6.3. And it was the third topic. It's section 6.3.3. It's the third topic or the third subsection of that section. Okay, so in section 5.2, we've done a lot of reviewing because everything's pretty much what we've done before with a slightly different name or a slightly different perspective. The one big new thing that we did was we talked a little bit about what odd and even functions are. Now, we haven't completed that discussion. We're going to have to come back and talk about it a little bit more once we know how to graph sine and cosine. So that was our one really big takeaway from this section. Everything else in 5.2 has pretty much been reviewed. The good news, at least as far as I'm concerned, is that 5.3, the next section we're going to look at, is about trigonometric graphs. So we're going to be starting learning how to graph the trigonometric functions. The good news for you is that that doesn't happen until after the exam. So we're done with the content for this first unit. Now you'll take an exam that covers everything we've talked about so far. And when you come back, when you start again on the other side, we'll be talking about graphing the trigonometric functions.